Hello and welcome friends in yet another lecture of digital electronics and microprocessor. In previous lecture we have started with the sequential circuits where we have covered the difference between the combinational circuit, sequential circuit, and after that we have seen the block diagrammatic difference between the combinational circuit and the sequential circuits also. Next, we have completed what is the difference between the type of sequential circuits like synchronous and asynchronous circuits. Then we have seen the astable, monostable and bistable multivibrator circuits also. Now, in this lecture, we are starting with the content of 1-bit memory cell because in last lecture we have covered the point of memory element which is acting as a basic building block for any of the computer elements. So today we are starting with this 1-bit memory cell. As just I have said, 1-bit memory cell is nothing but a fundamental building block for any computer memory because these memory cells are going to store a single bit value of digital representation into its location for the specific time period. These electronic circuit will store one bit of binary information. Generally, this information will be either logic 1, which is indicated by the high voltage level, and this will be said to be a memory cell's set state. It is said to be a set state for a memory cell. While the logic 0 level, which is represented by low voltage level, is said to be the reset state for that memory cell. And that's why, in short, we are saying that a single bit memory cell can change either to the two states of set or reset. And this value of cell will be assessed by reading that value. And that's why here the block diagrammatic 1-bit memory cell representation we are going to have, where we can see there will be two basic inputs in which one is actual input which is to be stored in the memory, and this is right terminal which is said to be the control input for that memory cell. And this memory cell can be implemented by using the different technologies such as bipolar, MOS and other semiconductor devices. Because you might be knowing that a simple transistor can be acted as a switch, and transistors are nothing but the bipolar devices itself. Why it is called as bipolar, that you people have studied in the basic electronics as well as for analog circuit design case. But only here you can refer the case that the transistors or MOS can be used, or any another semiconductor devices can be used for storing a memory, or that can be used as an memory. So it will store one bit of binary information and it can be accessed by reading the cell. So what is the reading of the cell is there? That is nothing but retrieving the stored information from the memory location, while writing to the memory will indicate that we are putting the some information into that memory location. And that's why we are saying that it will be set if it is storing 1, and it will be reset mode if it is storing the value as 0. Now, once again, we will come to the case of latch. because I have mentioned that memory elements will be either the level controlled or level triggered or edge triggered devices. And these level triggered devices will be named to be the latches, while edge triggered devices will be named as flip flops. So we are turning first towards in detail study of the latches. These electronic logic circuit that has two inputs and one output, and one of the input will be always called as a set input and other input will be called as a reset input. So generally for the latch, set and reset, these are the two inputs, and these latch circuits which are performing, they will be either active high latch circuits or active low latch circuit. But definitely these latches are also going to store every time a single bit information. Why? Because here we have stated that this latch will have two inputs but output is only one, and that's why we are saying that latches can store one bit of information. Basically, there are four different types of latches, and these latches are defined based on what are input values. That means if inputs are set and reset, it will be called as SR latch. If only D input is present, it will be called as a D latch. If the inputs are named as J and K, it will be named as JK latch. And again, if only one input named as D is present for the given latch, then definitely it will be called as a T latch. And the major difference in these all latches is types of the number of inputs they are having and how many number of states they are going to change. So we are starting with first latch, which is SR latch. So the name will indicate the input parameters. So this latch will have S and R inputs. But here this latch will possess two different outputs which are named as Q and Q bar. When in this the Q output is high, the latch is said to be into the set state, and if Q is in the low level, then the latch is set into the reset state. And if I am saying that active high input SR latch is present, then this is defined or obtained with the help of the NOR gate, and that's why this SR latch can be also said to be the NOR gate latch, in which based on the two input combinations the two output states are to be defined. And for that case we are having, if suppose R input is high, but along with that S input should be low. If both these are satisfied, then and then only the latch will be in reset state. On the contrary, if the S input is high and R input is low, this latch will be in set state. But if suppose R and S both inputs are low, then there will be no any change in the state for the next incoming clock value. But if both the inputs are high, that is R and S are high, then Q and Q dash both are low or they are invalid. But if suppose the latch is active low latch, so that active low latch will be indicated as S dash R dash latch. This dash will indicate here the operation which is performed when input level is low. And such like low level active low input will be implemented by using the NAND gates. And that's why here, instead of R value 1 and S value as 0, we will have now the condition which is exactly opposite, that is R dash will be low and S dash will be high, which are complements of previous R and S values for getting the reset state. In the same way, to get the set state, as compared to this here, S value should be low and R value should be high. And that's why here you can see that R dash value is high and S dash value is low. And this will be obtaining the set mode of operation for that given latch. Now here, when both the inputs are high, that time it is indicating the no change. While in this case, when both the inputs were low, there was no change. Similarly, when both the inputs are low, in this S dash R dash latch, the Q and Q dash both will be invalid or they will be high. And that's why here, for SR latch, the drawback is going to occur. Either you implement SR latch or S dash R dash latch. That means the NOR gate implementation or NAND gate implementation of the latch. In those cases, we will find out the invalid condition which is going to exist. And that invalid condition is not able to avoid. So here we are presenting the block diagram representation of SR latch and S dash R dash latch. So here you can identify that on the input side of SR latch, as they are active high, so no bubbles are present over here. But as S dash R dash are active low, because of that on the input side, as like this, the bubbles are going to be present. While for these latches to be active high or active low, output will be Q and Q dash only. And that's why here on the output side, either it is active high or active low input latch, the outputs will be specified as Q and Q bar. The characteristic table for these latches will indicate the combination of R and S inputs which are to be applied, and corresponding to that what will be the Q and Q bar outputs. And what we have discussed in words in the previous two slides, that only we have presented here when in the form of table that we have presented. That means for active high SR latch, when both inputs are 0, the present state will be the previous state value only. Or in other words, I can say the previous value will be continued to be the present state value. When S input is 1 and R input is 0, Q value is 1 and Q bar is 0, which is said to be the set condition for the latch. On the other hand, when S is 0 and R is 1, the Q output is 0 but Q dash output is 1, which will indicate the reset condition or reset state of the latch. But when both the inputs are 1, the invalid condition of the outputs, that is 0, 0, will happen. But on the contrary, when the active low input S dash R dash latch we are going to consider, exactly opposite to this situation has to happen for each of the case for getting set reset, no change and invalid condition to occur. So here complement of 0, 0 is 1, 1. For getting the input of 1, 1, the no change state will happen. While in S and R, the state was 1, 0, but here it will be 0, 1, which are complement of S and R respectively. They will give you the set mode of operation. Similarly, when 1, 0 is the input for S dash R dash, it will give the reset condition, and when both the inputs are 0, 0, it will produce the invalid condition of 1, 1 output. So here is the presentation of the NOR gate implementation of SR latch, which are active low, and these are the NAND gate implementation for active high implementation values. And that's why you can see here active high input is SR latch input condition. When S is 1, R is 0, it is in set state. When again after this 0, 0 will be presented, we know for 0, 0 input, the previous state will be continued and previous state output will be 1, 0. That's why it will be continued in the next state as a 1, 0 itself. Next, suppose the input is 0, 1. So when 0, 1 is presented, S is 0, that means it is in the reset state. So the Q dash is 1, but Q value is 0. And after this, suppose again 0, 0 input is presented, then this previous state will be carry forwarded as a next state. But if suppose after that 1, 1 is a input value, then it will change to the invalid state. And this we can check for this NOR gate implementation case. While this NAND gate implementation will show us exactly the opposite results to this of the active high implementation. And that's why this is a truth table corresponding to the NOR gate implementation of SR latch, and this is a truth table corresponding to this NAND gate implementation, where for this R and S inputs, what are the Q and Q bar outputs that has been represented in the form of a waveform, and the different state representation for these waveform values. So we know that if R is 1 or S is 0, that state will be said to be the reset mode of operation. And if that is a reset mode of operation, the Q output is always 0 and the Q bar output is 1. But this will be valid either reset is 1 or set is 0. So you can see here up to this level R value is 1 and because of that the Q output is 0. But after this instance the R value is 0 but set value is also 0. That means both the values are 0, 0. And if both the values are 0, until your S value is going to change, the output is not going to change in case of the Q value. Because if 0, 0 is present as an input, the previous output only is going to exist when both the values of R and S are same. And that's why until this instance when S is going to change, the Q output is persistently seen to be the 0 only. But the instance when S goes high, the Q output also goes high. And it will remain constant to be as 1 until your reset value will go high. Because if the reset value goes high, this Q output should go low. And that's why at this instant, when R input has gone high, the Q output has gone low even though the S input is high. And the situation when again here R input is 1 and the set input is 0, definitely the Q will have 0 output. And this is what with the help of these waveforms, we can get implemented or we can get described over here. But you can see the condition that when both R and S are 1 at the simultaneous instance. So here neither Q nor Q bar will be high in that situation. Rather than that, here we will see the continuous transition of both Q and Q bar outputs. And when such like this condition exists in SR latch, this condition is said to be the race around condition. When S and R both are 1 and because of that the output is said to be invalid, which is continuously going to change its level from low to high or high to low, and this condition is said to be the race around condition for the SR latch. So here we can see the presentation that when both the values of S and R as 1 and 0, that means this first condition, output is 1 and 0. Then the next situation, when S and R both are 0, 0, for that output will be continuously kept as 1, 0, which is the previous state output. For the third state, the S input is 0 and R input is 1. Corresponding to that, the output will change as 0, 1, which is indicated with this blue mark. Next is the output which is going to change as 1, 1, and for that 1, 1, the orange color marked output which is going to be obtained is 0, 0. And that has been presented in this truth table as well as in this graphical representation. Now, there is one another concept apart from active high and active low SR latch, and that concept is said to be gated SR latch. Here this gate is nothing but a control input, and based on that control input, here the states of SR latch are going to change. That's why here for implementing this SR latch, we are going to observe instead of two inputs, one extra input of enable is going to be introduced for getting the SR latch outputs. And this output will be generated with the help of the two NAND gates. So it is said to be the gated SR latch. In this situation always, the output value QQ bar are going to change only when the enable input is high. If the enable input is low, the output states are not going to change. And here, whether the invalid state is going to occur or not, that also we have to check. So we can see here that the output Qt, that means present state output, is 0. If the present state output is 0 with the enable value as 1, then with the SR output, input to be 0, 0, it is said to be the no change state with respect to this characteristic table. So here the Qt plus 1, that is next state value, is also 0. Now Qt is 0, but S input is also 0 and R input is 1. As S is 0, that means it is in the reset mode. That's why the Q of T plus 1 is obtained as 0. In the next state, S value is 1 and R value is 0. The Qt output, that is present state, is 0, but S is 1. Because of that, the next state will change to 1, which is said to be the set state. If suppose this Qt is 0 and the S and R inputs both are 1, definitely it will be indeterminate. Now the next case we are going to occur or we are going to check, and that case is if suppose instead of Qt being 0, the Qt output was 1. So what change will happen? So as the present state is 1 with 0 inputs to be applied, this present state will be applied as the next state, so the output will change to 1. Here the output which is present output is 1 but set input is 0, and because of that this will change to the reset mode. Next, even though present state is 1, S input is 1 and R is 0, that's why it will go to the set mode. In the next condition, the present state is 1 but S and R both inputs are 1. Because of that, it will go to the indeterminate stage. So here, from this truth table, we can get the equation for the next state in the form of the inputs that are provided as well as the present state output. So here you can observe that Q of t plus 1 is obtained as S plus R dash Q. So this Q is nothing but Qt. So let's check the condition. The Q of t plus 1 is 0. That means this left hand side is 0. So whether it is obtained to be 0 with this equation or not, that we have to check. So S value is 0. So 0 is ORed with R dash. R dash is 1. 1 ANDed with 0. That means it is 0. So 0 ORed with 0. So resultant is 0. The next case we will take. This is 0. Its complement is 0 and it is ANDed with 0, and this 0 ANDing result will be ORed with 0. So resultant is 0. Next, S is 1. R dash is 1 but this Qt is 0. So S is 1, 1 ORed with 0. Resultant is 1. The next state, S is 1, R dash will be 0. 0 ORed with 0 is 0 and that 0 is ORed with 1. So it will be Q of t plus 1 which is indeterminate value. This is how this particular equation will be said to be the characteristic equation for getting the output or next state output to be defined for this gated latch. Next is gated D latch. As in the name only D is present, and that's why for this latch only one input is present. So if we are going to compare the gated SR latch and gated D latch diagram, the change what we are observing is going to lie on this input side, and that will be corresponding to this D connection. That means the connection going for first NAND gate and the connection going for this second NAND gate. Let's observe for this. Here for first NAND gate in the gated SR latch, input is S along with enable, and for second NAND gate input is R along with the enable value. But as in the gated D, instead of S and R inputs, only one D input is present. So for the first NAND gate, it will be given in original form as D along with enable input, while to another NAND gate, it will provide the enable input as well as the complement value for this D. The remaining part of the next circuit is kept same as that of in the previous gated SR latch. So there is no change. Only change what is observed is on the input side of this gated latch. And that's why here we have written that make R input equal to S dash. That's why we are saying here that R input in previous case has been made as the value of this S dash, which is complemented form of initial input. And this is done to eliminate the undesirable condition of invalid state in the SR latch. So let's check out how in the gated D latch for the SR latch invalid state or indeterminate stage is going to be removed. So in the operation of this D latch, we are seeing that when the enable is high, that time if D input is high, then only the Q output will be high. Otherwise, the Q dash output will be high. And when Q output is high, the latch is said to be in set mode. Otherwise, the latch is said to be in reset mode. And so we are saying that when enable input is high, the Q is going to follow the data input. And this is what has been presented over here. If suppose I am observing that active high level for this, then at the active high level, what is the D value it is going to check? If the D value is high, then the Q output is also high. And this will be going to change when the value of D is changed at high level only. That means in this duration we can observe that when the level of clock is high, at that time the D input value is low, and because of that the Q output has been changed to the low value. In the next case, when this yellow marked portion we are observing for the high level representation, D input still is 0, and because of that the Q output will be 0. But in this next case when we are following, as the clock level is high, and when the clock level high is going to start, we are observing that D output is high, and until the D input is high, during the period of clock input is high, the Q output will be also high. But the instance when D will become low, according to this D as a low value, during this clock as a high level, this Q output also is going to change. And that's why here in a truth table or characteristic table of this latch, we are saying that when enable is high, according to D, the next state is going to change. That means with En value as 1, if D value is 0, the next state will be also 0. With enable as high, if D value is 1, the next state will be also 1. But if enable value is 0, whatever may be the D value, the next state will be no change, because here in the case of Qt plus 1 to be changed, always the enable value needed is to be 1. And that's why we are saying as a characteristic equation for this D latch that when enable input is 1, the next state always follows the D input. Always follows the D input, which has been represented into this particular waveform representation. But we are seeing that these latch circuits are not suitable in any synchronous logic circuits, because generally here we are observing that whenever the levels are going to change, that time only the outputs for these latches are going to change. In short, we can say when the enable signal is active, according to that enable signal only, as the excitation inputs will be presented to the gate, that will be given as a Q output. So, any change in the excitation input is going to immediately cause the change to be occurred at the latch output. And this is true if and only if the enable is active high. This problem is going to be solved in the memory element circuitry by using the spatial timing control signal, which is known as a clock. And this clock is going to restrict the times at which the states of the memory elements are going to change. And because of this, now we are leading towards the age-triggered memory elements, which are nothing but flip-flops. So up till now, the latches, which are the level-triggered elements, memory elements that we have covered. But as we are knowing that the problem is going to exist, that the latch outputs are going to be present only if the gate input is high. Otherwise, it is not going to change. And to solve this problem, we are going for applying a clock input signal instead of the gate control input signal. And that's how in detail we are going to cover in the next lecture of the flip-flops. So right now for today we are stopping with this definition of the flip-flops, why the flip-flops are needed and how the flip-flops are to be evolved.